Okay, so here we are for the final lecture of Structures 1. Hopefully I'll get to see all of you again next year in Structures 2. I want to apologize again that I've been trying to get your lectures posted on Wednesday, even though the deadline is noon at Thursday. The kids, everything I predicted happened right after we went back to school and everything, after kind of more or less recovering from COVID. We isolated for 10 days instead of just 5. Um, the kids brought home the other cold or sickness that's been going around. So we kind of just got back on our feet like today-ish. We thought we were free and in the clear last week, and then we basically lost almost a whole other week. So I really appreciate how patient you guys have all been. This is something that I've been reflecting on. I remember when I was in university and people with kids always being like, you don't understand how hard it is. Like, you don't get it. And I remember thinking, well, that's kind of a crappy thing to say. And I still think that's a crappy thing to say. Yeah, it's hard. What I'm trying to do right now is hard, but I also think what you guys are trying to do is hard, and the two don't negate each other. Maybe the message is it stays hard forever. I don't quite know, but I want it to be acknowledged that everything you guys are trying to do is exceptional, and I'm just so thoroughly impressed with what you guys are trying to do during this pandemic. So thank you for your patience with me, and hopefully I've been giving you guys the same in return. Exam coming up. You guys are April 22nd from 2 to 5. That is posted in the exam timetable on the Daniels website. That is how I know about it, the same as you. I do get an email, but it's after it's already been posted. So I will, leading up to the exam, provide you with an appendix which has the relevant pages from the majority of those PDFs that I've shared with you throughout the term. The idea being that if there is one that has 60 pages and I only give you 2, probably the information you could possibly need to complete the exam would be in those 2 pages, and that's it. If you are finding that you need something on another page, it's possible that maybe you're going down the wrong track. So work hard with those 2. I'm sorry, are you in a meeting? Am I?
No, I'm just going to charge up, get ready for my next meeting.
Okay. We're battling for the prime office space today, as we're both trying to make up for so much lost time. So we've been working on a second office forever, and it's going to be done just after we both need a second office all the time, because he'll probably be going back into his real office eventually. Going back to the exam, it's open book. So yeah, I'm giving you that appendix, but that's hopefully to kind of get you through 90% of the questions. Preparing for an exam like this, what I would strongly recommend is to go through and, at least while studying, pretend it's not open book. And what I would normally do is like have 2 or 3 sheets of paper that I would write out all of the like quick things that I think the professor might like. I have given you lots of hints. I like lists. So remember those lectures on concrete and steel where I talked about what was better and how we do those things? Yeah, I really like the lists in that. Advantages and disadvantages, the best kind of structure to build out of each material. Those make fantastic exam questions, especially on Quercus, where it's kind of really hard to give you guys any leeway. Like, the Quercus has to be precise. I like equations, so write out any equation you've seen me write out. And then there were a few fantastic diagrams that I talked about that make great exam questions. And so if you saw in the slideshow, great exam question, I can guarantee you it's on the exam. They asked me to try to limit cheating. Not that you guys are grad students. What would you possibly gain from cheating? I can't even imagine, except being screwed when you finally go to work. That said, what I've done is if there is a particular kind of degree of difficulty of question about a particular topic, I have 2 or 3 versions of that same question that have slightly different answers. And so that's to like share out difficulty so somebody doesn't end up with all the hard questions and somebody ends up with all the easy questions. That doesn't seem very fair. So I make question pools, and you'll get questions out of each of the pool for each question type. Obviously, there's going to be math, so make sure you have your calculator on hand. I know you could use your phone calculator, but even I find they are crap. So try to get your hands, make sure you have in front of you a good calculator. I know there's been questions about do I monitor if you leave the screen and if like tracking mouse movements. That's way too much work for me. Why would I do that to myself? And again, you're grad students. If you've gotten this far by cheating, you're better at scamming the system than I am at catching you. And the only person you're doing a disservice to is yourself. So do what you need to learn this material. That's what I care about. I want you guys all to do well on this exam. The projects are due the last day of the term. I can't remember if this year that's the 29th or the 30th, whatever it is. So there's a hard deadline that you have to upload your projects to. In the project description, I tell you how to write your file name. I am not doing that because I'm an absolute weirdo. It means that I can see at a glance that everybody's submitted. It allows me to go through a quick checklist that the projects have been submitted, and it helps organize it for me when I'm marking it. So it saves me a ton of time if you take 2 or 3 seconds to save your file name the way I've suggested it. So the FTP site should be up and running. I'll go back and even double check that later today. All of that to say is I will not be downloading the projects until 9 a.m. on May 1st. There's a hard deadline. I am not telling you to go past that deadline, but I'm telling you that I won't be checking what's there until 9 a.m. on May 1st. So as long as everything's there at 9 a.m. on May 1st, I'll be happy. If it's not there at 9 a.m. on May 1st, I can get in trouble because I have to submit all the marks by, I think it's like 5 p.m. on May 4th. So I have the 1st, 2nd, 3rd, and 4th to mark both of your projects, so part 1 and part 2 for all of your class, which is like 65 students, I think, plus project 1 and 2 for the structures 2 students, and there are 90 of them. So I have a gigantic amount of marking to do. I sequester myself. I get my husband to drop me off by boat at our water access only cottage that has no insulation. I light a big fire, I stock the fridge with food, and I start marking at 9 a.m. on May 1st, and I will put in like 13-hour days until I submit the marks. So I'll be isolated just marking, but I need those marks, I need those projects there then. I will have some access to internet, but it's not great because I am squirreled away doing all the marking. Okay, so today's final lecture, there's kind of one last lesson I want to go through, and it's more of a, as much as I will have a question about it on the exam, it's actually a super practical one, and it's one that I think even architects practicing today would benefit from. What are the quick thoughts around moment frames? And next term, or next year when you do structures 2, you're going to be so tempted to use moment frames everywhere. A Virendale truss is basically a truss with moment frames. You guys are gonna want to solve the world with moment frames and Virendale trusses, but I'm gonna show you why you would only do it as a last resort, okay? We're gonna work through a problem solution for a moment frame. Then we're gonna look at comparisons between moment frames and brace frames. And then we're gonna talk about moment frames for a few minutes. And then the last few slides of this are some worked out examples, and then kind of a quick little blurb going back to the project again for a second. I have also posted online what if we were allowed to have assignments the last 2 weeks, it is the assignment I would have given you. You're not allowed to have assignments because we can't have submittable marking information there, but I know some people like more studying material. So I have provided what would be an assignment, but with all the solutions worked out. So you have it there as a solution set. At the end of this lecture, there's even a few more problems that I've worked out. So by the end of this, you're going to have like 20 worked out beam solutions that I have done for you. And I can tell you that in your project, part 2, that you're going to be doing the easiest type of that. You're still going to have to do the work, but there should be no excuses for you guys not to get absolutely fantastical, beautiful marks, because I've given you fully worked out solutions for projects and problems that are so similar to what you have to do on the project, okay? So let's go through this. All right. Do you remember a few weeks ago when we solved a braced frame through method of section? And we had axial forces in all of the elements for a braced frame that was 8 meters wide and 5 meters tall and had a pinned base. So for that problem, we had pins here and a brace. So for whatever reason, maybe there's a door here, there's a big window. They didn't want a brace there, and they've said, okay, what does it take for this to be a moment frame? What does that look like for us if this turns into a moment frame? Now, you'd think I would learn to have these on hand. Okay. So, if this was our braced frame, if we say, okay, we want to take this out here. All right, so we take that out. That's not very good. If this is what's holding our building up and we take away that braced frame, we've got a problem. So what we need to do is essentially glue these joints together. So right now these are pins. You can see how they don't prevent rotation. So you can see the angle there changes. So what we're talking about is gluing here and here. And if we glue those together, we have a moment frame now. I don't have a way to, I'll see if I can build one of these where those actually get glued together to prevent that rotation. That is a moment frame. Okay, so we have 250 kilonewtons applied to it. We have 4 reactions at the bottom. We have our 2 gravity ones, so in the y direction, but we also have 2 in the x direction. We only have 3 equations available to us. For the other one, when we did it with the brace frame, we saw that there was actually no way to have on this one over here an x component, because there was nothing that could apply an x component to the base here, meaning we technically only had 3 unknowns. We knew that it had to be 0 over here, because those could only take axial loads. Well, we have something a little bit different here now. We have a moment connection. So we're actually going to have 4 unknowns down here, meaning we're technically something that is statically indeterminate. Statically indeterminate means that we have more unknowns than we have equations. Now, if we look at this, what can you guess is the issue here? Actually, Dave, can you do me a favor?
Yeah.
Can you push me? Yeah, I wonder if I can push me right here. All right. If Dave's pushing me, I can feel that both of my feet are engaged. If I went up on my tippy toe on this side, things start to get a little bit different. Thank you. I thought that was going to be more effective, but it was not. But you know that your feet are sharing out that friction load. Think of this X reaction as a friction load here. There might be something more physical there, but it's the same idea. We're going to make an assumption that the X component of these reactions are equal. I, as an experienced engineer, am going to tell you that most of the time that is true. And I am going to show you using modeling software later in this lecture when it isn't true. Okay? This problem here, it's probably true. We don't know exactly what's going to happen, but we're going to start with the base assumption that that is a truth. I know you're thinking, you're telling us to assume something that's true, and then later you're going to tell us when it's not true. Hopefully it'll be clear when I go through and explain what makes it not true. Most of the time it would be true, and in a little bit I will explain when it's not true. So let's go through what we know about solving problems with method of sections, okay? So we did this as a braced frame a few weeks ago. That's not better. That's way worse. All right, that's not so bad. Okay, we did this a few weeks ago with the braced frame, and now we're gonna solve it with the moment frame. All right, let's take a look at our problem set here. I need to put my hair up because it's getting absolutely ridiculously long. And I'm lazy, so I don't go to a hairdresser ever. Okay. All right, you guys are all gonna forever think about that wacky teacher that talked about all of that nonsense stuff. I guess it's something, right? All right, let's draw out our frame here. We know that there's a moment connection here. When we draw this pin, we tend to leave a little bit of a gap there, but we know that this is a moment connection here. We know that for a moment connection, we'll often draw that in as solid filled triangles, just to kind of remind ourselves that, hey, it's like those are glued together here. We know that this is 5 meters tall, and 8 meters wide. It's the lateral load resisting system, and so either wind or earthquake is causing a lateral load on this of 250 kilonewtons. We know we have two pinned reactions here. We have RY1 and RY2, and we know we have two X reactions here, RX and RX, and we are starting with the assumption that RX equals RX. We're dividing out the reaction equally between these two. We are saying that we think these two things are going to share the load equally. Whatever that load is, we're saying we think we're going to have those shared equally. This is our assumption. Okay? This is going to allow us to only have three unknowns. Because look, we have RX and RX, RY1 and RY2. So we only have three unknowns, which means we can make use of our three equations. I know, crazy. I'm telling you to take this on trust a little bit. There are ways to do this problem solution set, not assuming these share out equally. And I'm going to show you that under certain circumstances, if we go through that process, the long, hard, complicated way, we will see that in certain circumstances, they are equal to each other, okay? So let's go through, and what's the very first thing we do with this? Right, we solve for our reactions. Okay. Sum of the forces in the X direction, where everything going in that direction is positive, and we want this to be in static equilibrium, which means it's not sliding back and forth, or that the sum of all of the forces have to be zero in that direction. Well, we have Rx plus Rx minus 250 equals 0. So we have 2Rx, bring that over, make it positive, divide the 250 by 2, and we get Rx equals 125 kilonewtons. Essentially, that's the assumption we made. We said we're going to share that load, that 250 kilonewtons of sliding, out as a reaction equally on each side here. Okay. Now let's sum the moments about the z-axis where everything spinning in that direction is positive. Do you know what I didn't do here? What I like to do with trusses or braced frames or moment frames is label out my members. So let's call this member A, this member B, this member C. We'll call this node 1 and appropriately call this node 2. This is RY1, RY2. And let's call this node 3 and this node 4. Okay, that's just to help us think of that as an accounting process. That's just to help us keep track of our numbers because it's so easy to lose track of things. You've seen me do it. I'm sure you guys have done it. It's a very frustrating feeling when you've done everything right, but you made some silly little mistake. You get the wrong answer, not because you don't understand the process, but because you made a simple numerical mistake. Unfortunately, because everything is online, it's hard for me to award points for that. Normally, what I used to do was actually go through and visibly look at assignments and exams for those problems. But being online, that's a very hard thing to do. So we have to be really precise. It's more like what it would be in the real world. Let's spin about node 1. So let's assuming we're saying we're putting our imaginary thumbtack right here. That's where our imaginary thumbtack is. Okay, well, RY1 passes through our thumbtack. RX and RX both pass through our thumbtack, leaving us with 250 kilonewtons and RY1 trying to make this spin. Okay, 250 kilonewtons is trying to spin this in this direction. Let's follow the path of the 250 and see how close it gets to our node. Follows along this path here. Okay, well that means it's going along this track. It gets 5 meters away from our thumbtack, which is right here. So it's trying to spin in that direction. Curl my fingers in the direction it's trying to spin it. My right hand then tells me if my thumb is in the positive direction that it's a positive moment. So plus 250 times 5 meters. I also have RY2 trying to spin this. It's trying to spin it in that direction, which is positive, so plus RY2 times its distance away, which is 8 meters. We only have one unknown in this problem. We can rearrange this and solve for RY2. 250 times 5, bring it over, make it negative, and divide by 8. Divide by 8. 250 times 5 divided by 8 minus 156.25 kilonewtons. The minus tells us that we assumed wrong. We assumed that this was in compression right here, or that this reaction was a supporting reaction. Instead, it looks like it's trying to hold it down. This is trying to kick up, and so we're pulling down at this spot. Again, if you stood up and had someone push you, you could feel that with your feet. Okay. Let's now sum our forces in the y direction with everything upwards being positive, and we want this to be in static equilibrium, or we don't want it to move up and down, or the sum of all of those forces must be 0. There's 3 ways to say the same thing. We have RY1 going upwards. We have RY2 going upwards, but we've calculated that it's minus 156.25. That's it. It's only our reactions. So that means RY1 equals plus 156.25 kilonewtons. Okay, so this load gets shared out between those two as a reaction in the x direction. And then here, this side's trying to kick up, this side's trying to push down, and they're equal and opposite forces. Sorry, thank you.
No problem.
The students all thank you. Say thank you, Dave. Okay. Now, let's start the fun part. Let's start method of sections. Let's do method of sections, cutting through member A. Some unknown distance through member A. So, method of sections through member A. Okay. There's our member A. We know at A, we have a reaction of 156.25 kilonewtons and 125 kilonewtons. And that's it. Those are the only applied loads if we're cutting here. I'm going to work around this frame, cutting through A, then cutting through B, and cutting through C. You could go the other way. That's totally fine. You'll end up with the same answers. But I'm lazy and I like to have a method. So I'm going to cut through A and get rid of all of that. Then I'm going to cut through B and get rid of all of that. Basically, I'm always going to keep the left-hand side. But we know that something must be holding this in place. This is in static equilibrium, which means this must be in static equilibrium. So what's happening at this point right here internally on this member to make sure it's not flying off in space or spinning? Something is happening there. Okay, so what could be happening there? We know that there could be 3 different internal forces. We know there could be shear, moment, and axial. In trusses, I told you we were only looking at axial loads. And in our beams, we were only looking at bending and shear. This one's slightly more complicated in that we can have all 3 things happening in it. How would you know when to do that? Well, some of that comes with practice, but I'm going to tell you if you have moment connections on things with a force in the other direction or along its length, you're going to end up with 3 types of forces internally on things. That's beyond you to be able to figure that out. I'm telling you that we can have all 3 on this. Well, I always draw my unknown axial force as a tension force. So that's my unknown tension A. I always draw my unknown shear like that, and I always draw my unknown moment spinning in the positive direction. So I have 3 unknowns here. Lucky for us, we have 3 equations to solve this. All right, let's start with summing the forces in the y direction where everything upwards is positive. We want to know what it takes for this to be in static equilibrium or for the sum of all of the forces to be 0. Okay, well, we have A going upwards, and we have 156.25 kilonewtons going upwards. And that's all that's going in the y direction. We can rearrange this, and A equals minus 156.25 kilonewtons. We assumed A was in tension, so this negative tells us that we got it wrong, and A is actually 156.25 kilonewtons in compression. And I think intuitively you can understand that. If you were standing here with your legs like this and someone pushed on you, you can feel that this leg is pushing down and this leg is trying to lift up, meaning this would be in tension and this would be in compression. So I think intuitively that matches what you expect. And this is why I think you should always, before you start solving anything, take something and play with it. See what you think is going to happen. Okay, let's sum our forces in the x direction, where everything going in that direction is positive. And we want to know what it takes for this to be in static equilibrium, or for the sum of all of the forces to be 0. Okay, well, we've got our unknown shear in the positive direction and 125 kilonewtons. All right, we can rearrange this, and V equals minus 125 kilonewtons. Remember, for shear, Positive or negative doesn't really have much meaning. It's important for tracking our data, but when we're looking for maximum values, the absolute value is what we care about. So with axial, it tells us whether tension or compression is what we have, which is really important. And you're going to see that next term when we do our capacity of things, that axial, whether it's tension or compression, has a real impact on things, but positive or negative shear doesn't. We like to keep track of it while we're solving our problem though. All right, and the third one, let's sum our moments about the z-axis where everything in that direction is positive, and we want to know what it takes to be in static equilibrium. And we have cut this some distance x. I, being lazy, always solve my method of sections at the cut, so I put my thumbtack at x. So I'm cutting this at x, and I'm putting my thumbtack here. Well, my unknown shear passes through it, so it doesn't cause it to spin. A passes through it, and 156.25 passes through it. So I've gotten rid of A, this value, and V because they all pass directly through the point of my thumbtack. To be a moment, you need a force and an eccentricity, or a distance away. So those ones cannot cause a moment about a thumbtack right here. What we're left with is 125 kilonewtons, trying to spin our element in that direction, which is positive, and our unknown moment, trying to spin it in a positive direction. So we have plus moment plus 125 times. Remember, to be a moment, you need a value and a distance. Well, our distance is x. We can rearrange this and we can solve for m. M equals minus 125 x kilonewton meters. Well, let's just plug in a few values here. What is m at 0? Well, m right here at x equals 0, 0 times 125 is 0. M at 2.5. M at 2.5, so if x was 2.5, we have 125 times 2.5, so minus 312.5. And what is m at 5 meters? Remember, this thing could be 5 meters long. 125 times 5 is minus 625 kilonewton meters. So we now know what the moment is anywhere along member A. And we can see that it's the highest right here where it connects to member B. Remember, if there's a moment there, it has to go somewhere, meaning that there needs to be a moment connection between these two things. Okay, so now we know that we would have to design this connection for at least 625 kilonewton meters. Let's do our second section. Let's do method of sections on B. All right, so we're going to cut some distance x along member B now. All right, I'm lazy and always try to draw the same setup here. All right. I'm going to cut this at some unknown length along B. This is 5 meters, and this is distance x. We know that we have a reaction here of 156.25 and a reaction here of 125 kilonewtons and kilonewtons. And there are some unknown internal forces here: an axial force, a shear force, and a moment. And those three things are unknowns. We know that this object as a whole isn't moving or spinning, so this section of it can't be moving or spinning because the other part of it is holding it in place. So internally, there must be something happening on that member. And so this is how we can find those internal forces. Okay, let's sum our forces in the y direction, where everything upwards is positive. All right, we have 156.25 going upwards, and we have v going downwards. Those are the only things in the y direction, downwards, so it's negative. We can rearrange this, and the shear along B is 156.25 kilonewtons. It's independent of the length of B, so everywhere on B, the shear is 156.25 kilonewtons. Let's sum our forces in the x direction. Okay, we've got 125 kilonewtons that way. And we've got B going in that direction, and those are the only things in the x direction. So we can rearrange this, and B equals minus 125 kilonewtons. We always assume everything's in tension when we're drawing it, so that a negative value, which tells us we assumed wrong, that's a handy way that for negative to always be compression. So B equals 125 kilonewtons in compression. We have one last handy dandy equation for us. We need to find that internal moment. So let's sum the moments where everything's spinning in that direction is positive. We're going to spin it about the z-axis, and we want this to be in static equilibrium. And let's pick point X to put our thumbtack. All right, I'm lazy. I always do it at my section cut. Okay, if I put my thumbtack right here, shear passes through it, so it doesn't cause it to spin. And the axial load in member B passes through it, and it doesn't cause it to spin. So I have my unknown moment, which is what we're trying to solve for. So plus m. Put my thumbtack here. We have 125 kilonewtons trying to make it spin in that direction. Curl the fingers of my right hand in the direction it's trying to spin. My thumb tells me that that is positive. So plus 125 times, this is the line of action of that 125 kilonewtons. It passes 5 meters away. Okay, and then I have 156.25 kilonewtons trying to spin it in that direction. Curl the fingers of my right hand, point my thumb, it's pointing into the page along the z-axis, so that tells me it's a negative moment. So minus 156.25 times x away. That's the distance. The closest it passes is along this plane right here. So times x. We can rearrange this, and we can solve for m equals 156.25x minus 125 times 5, or 625 kilonewton meters. So our location has an impact on moment. So let's test it at a few spots. What's the moment at x equals 0? So if x equals 0, we have 156.25 times 0 minus 625 kilonewton meters. What happens at moment, what's the moment at x equals 4 meters? So halfway. Remember, this was 8 meters long. What happens at the midpoint here? All right, 156.25 times 4 minus 625. 0. We have 0 moment at the midspan of that member. Okay, let's check it at x equals 8. So let's see what happens when we have 8 as our distance x. So 156.25 times 8 minus 625 gives us 625 kilonewton meters. Okay. So we've got some information now for what the internal forces are along member B. We have one more member left. We need to know what happens along member C. So let's put this right here so we have quick access to it. So method of sections on member C. All right, 1, 2, 3, 4, 5. 2, 3, 4, 5, 6, 7, 8. And we're going to cut it somewhere along member C. Okay. This is 8 meters. This is 5 meters. And this is our distance x. Remember, I'm kind of going around it like this, cutting it. So this is x equals 0, and this is x equals 5, because I've gone through and cut it in that direction. We know that there is a reaction here of 156.25 and a reaction here of 125 kilonewtons. And we've cut past the applied load now, so we know there is also 250 kilonewtons of applied load on this moment frame. And this is not sliding in space or spinning because this hole isn't. So what's holding this portion in place? Well, the rest of this is what's holding it in place. So there must be some internal reaction or internal forces holding this in place. I always assume everything is in tension. So an unknown axial force of C. We have an unknown shear force, V, and I always draw my unknown moment in the positive direction. So now we can solve for these internal forces for anywhere along member C. Let's do the same process. Let's sum our forces in the x direction with everything going in that direction being positive. We want to figure out what it takes to be in static equilibrium. Well, we have 125 kilonewtons going in the positive direction. We have 250 kilonewtons going in the negative direction. And we have our unknown shear going in the negative direction. We can rearrange this. V equals, bring V over to the other side, 125 minus 250, we get minus 125 kilonewtons. Remember, for shear, we don't put a lot of stock in positive versus negative, but we need it to be able to keep track of things. So we'll keep track of it, but when we ask about what maximum values of shear are, we don't care about positive versus negative. It's the absolute value we care about. Sorry, guys. Okay. Let's sum the forces in the y direction with everything upwards being positive. Okay, we've got 156.25 kilonewtons going upwards, and we've got our tensile force in C going downwards, so it's negative. Equals 0. We rearrange this. C equals 156.25 kilonewtons. The value is positive, which means we guessed right, and we guessed it was in tension. All right, let's sum the moments about the z-axis. Everything's spinning in this direction is positive, and we want to know what it takes for this to be in static equilibrium. Okay, so I am going to put my thumbtack at x. So I'm putting my thumbtack right here. V passes through it and C passes through it. So I've got my thumbtack here. We're left with 125 156.25, and 250, and our unknown moment. So we've got a lot trying to make this spin about this point right here. So let's start with our unknown moment. We always tend to draw it in the positive direction. So plus m. We've got our 250 kilonewtons trying to spin it in that direction. Curl my fingers. My thumb tells me that it is spinning in the positive direction. So plus 250, and it is x distance away. You know what, I'm going to write this down here just because it's a little, to give us a little more room. M plus 250 times x. We have our 156 trying to spin it in that direction. The thumb of my right hand tells me that's the negative direction. So minus 156.25. And it is taking place 8 meters away. So times 8 meters. Okay, we have our 125 trying to spin it in this direction. Curl the fingers of my right hand. That tells me it's the positive direction. So plus 125 times this distance. Look, it passes this distance away. So if that's the line of my force, it's passing that distance away. Well, that distance is 5 and that distance is x, meaning that distance is 5 minus x, or 5 minus x. And those were all the things trying to make it spin. We had 1, 2, 3, 4 things trying to make it spin. 1, 2, 3, 4 things trying to make it spin. Okay, it looks like we can do some math here. All right. M equals, let's bring everything over to the other side, minus 250x plus 156.25 times 8, so plus 1250, minus 125 times 5, which is 625, plus 125 times x. So I multiplied this out, but then brought it to the other side of the equation, so it changed the signs. So 125 times minus x, and then bring it over, became positive 125x. We can simplify this. M equals minus 125x plus 625 kilonewton meters. All right. Let's see what that means at various points along the length of this. So let's check it at m at x equals 0. Remember, this is 0 because we're cutting along this length. This is the length we're cutting here. So this is distance x. So that's when it's 0, that's when it's 2.5, and that's when it's 5 meters. So at x equals 0, which is right here, we have minus 125 times 0 plus 625. So 625. M at 2.5. We have minus 125 times 2.5 plus 625 gives us 312.5 kilonewton meters. And then M at 5 would be minus 125 times 5 plus 625 gives us 0. Okay, so we've got a lot of data about what's happening internally on this frame here, this moment frame, but I find that a little bit difficult to look at. Let's maybe draw a little set of summary diagrams here. Okay, let's draw our free body diagram. We're going to draw our so we'll make this one our free body diagram. We'll make this one our axial force diagram. And we'll draw our shear force diagram. I'm just going to put a note that I'm going to draw that in kilonewtons. And we'll draw our bending moment diagram. And that's going to be in kilonewton meters. Okay. This was 156.25 kilonewtons. I'm just going to draw this in the other direction. I could draw it upwards and keep the negative value, or I can drop the negative value and change the direction of the arrow. Both are valid ways to draw that. All right, we also then had 250 kilonewtons on this. And to be a free body diagram, you need all of the forces and all of the dimensions. Okay, so this tells us what's being applied to our frame here. And then we can start drawing our diagrams. Okay, our axial force diagram for our columns, this column was 156.25 compression. Our beam was 125 kilonewtons of compression. So if we come back and look at that, member A was 156.25 kilonewtons of compression, and member B was 125 kilonewtons of compression. And then I'll often change the color between compression and tension so it's visible at a glance. So 156.25 in tension. That just makes it really easy to see what's happening quickly. So both of these are in compression and that's in tension. Okay, let's draw our shear diagram. So member A had 125 kilonewtons of shear on it. Remember for shear, we need to keep track of positive and negative for solving our problems. But once we have it, we don't really care if it's positive or negative. Everywhere along member B, the shear was 156.25. And in our other column, we also had a shear of 125. So that's our shear force diagram. And then over here, we have a bending moment diagram. On member A, we went from 0 to 325 to 625. Sorry, 312.5. And this was 625. Now, it was actually minus 625. Again, now positive and negative moments mean a lot next term when we talk about top chord versus bottom chord of certain members. Right now, for this, it doesn't mean too much right now, but I'm gonna keep track of it so you can see it. The top chord, or the top member, we went from minus 625 to 0 to plus 625. Okay. Minus 625 to 0 to plus 625. And then our final member was 625 at x equals 0. And we went down to 0 moment at x equals 5. So as we wrap around this frame, we now have an image of what is happening everywhere on this frame. So it looks like our columns are always doing something similar to each other, while our beam switches up the shear and axial forces. So at a quick glance, somebody can see a lot about what is happening to this frame, which can be really, really handy when you're trying to make decisions about a large scale set of problems. Looking at all of these numbers, we need all these numbers to solve it, but it's hard to have a major takeaway. These images start to give us something that really lets us have a takeaway from our problem set. So there, we solved this system as both a braced frame and a moment frame. So let me turn this back up. Well, first let me make this small. And then we'll bring this back up. Okay. All right. Let's take a look at this. Okay, so moment frames. We've now solved this frame as a braced frame and a moment frame, and we saw that the braced frame only had axial forces in it, where the moment frame now had axial, shear, and moment that we had to design for. Let's see what impact that has. Now, you guys don't know how to check the capacity of things. Next term, you'll be able to say, okay, for this member right here, I know I need a member that can handle 125 kilonewtons of compressive force, 156.25 kilonewtons of shear, and 625 kilonewton meters of moment. Excuse me, sorry. But you guys don't know how to do that yet. You don't know how to pick the appropriate member. But I want to give you guys some takeaways about why moment frames are a last resort and what you can do with them. So I've gone through and I've taken this exact frame problem that we've looked at, and I'm going to show it to you worked out with modeling software that I use under a series of conditions. So let's take a look. So this is what I input in my modeling software. Okay, I could do all this by hand, but this does it really fast. So here's my brace frame. These little circles are just a shorthand way of the modeling software reminding me that those are pins. So there can be no moment transfer between any of these things. So no moment transfer can happen here because this is pinned to this column. These are drawn as pins. So this can only take axial loads, whereas this, they don't show you the solid triangle, but because there's no little dot, it's telling us it's moment connected, but it has pinned conditions at the base. So that means no moment can be transferred out down here. They are the same dimensions of 8 meters across and 5 meters high, and they both have the same applied load. We just went through and solved these problems. And we saw that we had a reaction of all 250 kilonewtons in the x direction over here. On this one, it was divided out equally. And we got equal and opposite 156.25 kilonewton reactions for these two things. Look at this, 124.99 and 125.00. We cheated and started with the assumption that those were equal. But that was a shorthand way of solving an indeterminate problem. What the software did was it went through and checked it at a series of assumptions to hone in on the one that works out. It brought into account the stiffness of the system. That's way beyond what we're going to do, but I'm going to show you some fallouts of that going forward. But you can see that this matches pretty darn close to our assumption. Right? They didn't make an assumption. They did it in a series of problem solutions. That said, they came out with our exact assumption. Pretty darn close, like a slight rounding difference between them. So this is what we did by hand. The modeling software gives us compressive values of 250 in this, 156.25 here, and a tensile force of, almost 295 kilonewtons in the brace. And then these match the axial forces we just solved. Here's our shear that we just solved. Remember, the braced frame didn't have any. And here are our moments. Again, because they solved this not making the assumption that these were shared equally at the bottom, their moments are pretty darn close to ours. Like if I told it to round to the nearest kilonewton, the answers would be the same as ours. So like a fraction of a difference between ours and solving this as an indeterminate problem, just because those base shears were the tiniest little bit different. All right, if we found members that worked for this, which is what we want to do, these two frames, for those shear force diagrams, moment diagrams, and axial force diagrams, these are the members that it would take for the reduced capacity to be greater than the factored load for all of those things. What are those members? You don't care too much about that. You can see that this is a lot bigger than this. And then look at this. This is how much the systems weigh, right? If what we care about is having the cheapest system, this one, and you could use weight as a pretty good indicator of cost, which is how people price out projects during the beginning phases. That's exactly what they do. They add up all of the steel, figure out how much it weighs, and then apply a cost to it. So this weighs more than twice this system, which means it's going to cost more than twice as much. So 2.5 times. So this costs 2.5 times this system. This is just meeting strength requirements. Remember, we have strength, stiffness, and stability. We have a free body diagram and a method of sections. We've analyzed it so we know it's stable. So it doesn't fly off into space and spin around in space. So stability, check. Strength, this meets all of its requirements and this meets all of its requirements. And this one weighs 2.5 times as much. But we have a third thing. We have stiffness we had to satisfy. Do you remember when I showed you stiffness requirements for lateral load resisting systems, or the heights of things, was H divided by 500 was what we had to meet for these things not to deflect too much out of shape, or else we'd start to crack our finishes and our windows would pop out of the frames. Let's look at the deflected shape of these two things. Now, I'm going to show you a deflection that I have increased the scale of the deflection so you could visibly see it. So, these are both at the same scale. This frame deflects 8.3 millimeters, and this frame deflects 56.3 meters. Our height is 5 meters, and our deflection limit is height over 500, or 10 millimeters. So this one works. Just meeting the strength requirement, we met our stiffness requirement for a braced frame. Our moment frame, however, looks like it's 5 times over for our stiffness criteria. Now, I have said that stiffness is a strongly suggested criteria, meaning if you don't have a good reason not to meet it, meet it. I would say probably 90% of lawsuits in things come over damages to finishes. So if you can say, but I met all of the criteria in the code, you'll be safe, you'll be fine. If you choose to ignore that criteria and there's damages to finishes, you might find a client that can come after you and sue you for something. So if you don't want to meet those criteria, you have to be very open and honest. And the owner has to understand the risk they're taking there. So if this was just an outdoor pavilion, maybe we don't care about that criteria because there's no damages on it. So like just like a pergola out in a backyard. Maybe we don't care, right? Because there's not really anything that can get damaged to it. But let's say this is a braced frame for a house and we want to make sure the drywall all doesn't crack. Like this is over 2 inches of movement over one story. You can imagine that's a lot. Okay, so if I went through and did the same thing but said I have to meet that 10 millimeter criteria, here is what the frames look like. Okay, my brace frame doesn't change, the same criteria I had before, but now these members get even bigger and even heavier, and look at this, it's more than 5 times the weight. So moment frames are not good for stiffness. They're really bad meeting stiffness criteria, which really drives up the cost of them. Okay, so 50 kilonewtons versus 8 kilonewtons, so more than 5 times the cost for this frame system. But we've now met our deflection criteria. Okay, so this now meets stability, strength, and stiffness. So both of these meet strength, stiffness, stability criteria, but this one now weighs more than 5 times this one, so way more expensive. Plus, moment connections are expensive. That alone has a cost and complexity with it. So it's not just more than 5 times, it's 5 times plus a more difficult connection. So here's a huge takeaway. Moment frames are bigger, they're heavier, and they deflect more. So even in that other one, we still had more deflection by meeting the criteria. The brace frame was performed even better than the criteria demanded. So we do not start with moment frames. Start with a brace frame. If you can find bays where you can put a braced frame, do that. It's going to make everyone's life simpler. If you have no choice and you have to use a moment frame, and that happens, we use moment frames. They exist and they're possible. But just try to be smart about when, where, and why you're using them, okay? I can guarantee you I'm going to ask you this question on the exam. All right. So let's take a look at what things we can do to a moment frame. So this is what we had with our original moment frame that met strength, stiffness, and stability criteria. So from now on, I'm going to try to meet those criteria. This weighed 50 kilonewtons. I had pinned supports here. What if I fixed the base? All right, so I made this a moment connection down here. So instead of just being able to take up and down loads and back and forth loads, I can take rotation out at this spot right here. Well, look at this. My weight goes way down. It's 23.9 kilonewtons. Except now we have to connect for a moment at the base. The foundations for this are going to be gigantic versus the foundation for this. So for the cost of steel, it looks like we've salvaged something here, except we've just deflected that cost to a different scope of the project. Sometimes that makes sense. If you have a project where steel has a high cost, or in getting the steel in is difficult, like if they have to manhandle this in, look at this, that connection looks like it's probably a little bit easier. So maybe that's a good reason to say getting all the steel out we can and transferring the cost into the foundations is a good idea. Well, what if we wanted to keep a pinned base here, but we wanted to try to reduce these member sizes? Well, here's a thing you can do. You could still moment connect the bottom of these columns, but instead of moment connecting into a foundation, we could put a beam across. So look at this. These members have gone down in size, and we still have a pinned connection for our foundations, which is great, but we've added a beam at the base here. So our cost has gone down a little bit, but now we have to either bury a steel beam or deal with that in some way. Now, this sometimes has this is a great solution in certain circumstances. If we're trying to do a retrofit in an old building where there's existing foundations and we don't want to put the moment connection into that, and we want smaller individual members so they can simplify and do a field moment connection, this can be a really good solution. I've done this a lot on retrofits on old houses where they want to put a big bay window in the back. Okay, remember I said we started with the premise that the reaction was equal at the bottom here. I, next term, am going to talk to you about the fact that stiffness attracts load. The stiffer something is in a system, more load will go to it than the less stiff elements. So the stiffer it is, the more load it'll attract. If these were both the same column, they would share the load equally, okay? Which is what the assumption we made was, that those were going to be equally stiff and share the load at the base. What if, for some reason, we had a narrower wall here and we had to hide this column in the wall? Or for some reason, we had a limit on what we could do here. You can see at a glance that you can see that if I try to bend this versus try to bend this is a lot easier to bend than this. So this is going to take more of the moment than this is, okay? So this is a much stiffer element than this. So more load is going to go over here. Let's see what that does to our axial, shear, and bending moment diagrams. Well, look at the reactions here. It's hard to see, but here we have our 125 and 125. We still have our same up and down values here and here, but look at our base reaction. This one is 185, and this one is 65-ish, more or less. There's some rounding in there. But you can see that this one has a bigger base shear than this one. That would have a big impact on us tracking our axial force, our shear, and our bending moments through the frame. Let's see what that does if we have not equal stiffnesses of our columns. Well, it didn't change the axial force diagram. Okay? But look at our shear. We have more shear in this member than we do in this member. And we have way more moment at this connection than this connection because more of the load is trying to come out through this column. So we can play with moment frames to try to meet the demands of the design criteria, for example. We still have to meet strength, stiffness, and stability, and moment frames are the worst case solution. But once we've made the decision to do a moment frame, there are ways we can manipulate things within it. All right, we talked about allowable deflections at the beginning of the term, and I just want to kind of bring that back into the conversation. Remember that they were about comfort and preservation of finishes. They could have an impact on stability. If we deflected too much, once we get to a certain point, it starts to turn into a tipping problem, or what we call P delta. Drainage, we can end up with a ponding problem, and it's about interface with building elements. So how our windows fit into our frames, for example. And I gave you guys some serviceability criteria for various materials, whether it was snow, dead and snow, live or dead and live, and whether it was susceptible to damage or not. Drywall, susceptible to damage. Plaster, very susceptible to damage. Glass, susceptible to damage. So what I've done, and I'm not going to work through these for you right now, for people, there's a lot of you that have already got this in the bag and know how to do all of this, but I've given you more worked out method of section problems. And I'm going to tell you one of them looks identical to what most of you are going to do in your project part 2. Okay, I have provided worked out solutions for solving B4, column B4, RJ01, RP02, RB11, and RB03. RB03 has a cantilever here, and these members are purlins that span from this beam to this beam, and then this beam spans to the tip of this beam. So there's a large point load plopped down at the tip of this member, so it's going to have an impact on the design. So I've gone through and done method of sections for all of these elements, so you can see some more worked out practical solutions. Now, these ones I've worked out. I also just want to talk about so this is the framing set that I gave you guys as like a typical building that is in no way typical because it does all kinds of crazy things and it's not what anyone would build. But it was really great because it expressed all the things that we could talk about structurally. On the second floor, we had 2B13. Well, look at this one. It has a column above with a large point load on it, and it changes what its load type is here and here. So we have one load type here, a large point load from a column above, and a different load type here. So you can imagine this one would be very complicated. And look at this, the snow varies over the length there. All right, here's the worked out problem for the column, because this column is picking up roof load and it's picking up second floor load, with some of it being from the low roof and some of it being from the high roof. I've gone through here and worked out the tributary areas, which are different on the different floors and for different load types. So because this one has snow and this one has live load and this one has snow, it's going to have a different impact on the members. So you can see I've gone through, I've figured out what all the loads are, and then for each section of the column, I figured out what the factored loads are. All right, and I've looked at the different load combinations to figure out the worst case load. I've then drawn the free body diagram of that column. This is the foundation. So we're assuming we're stopping at the bottom of the column, and then there's something happening here with reactions that transfer out into the foundation. And then here is my axial force diagram. This is exactly what I expect to see in your project. Anyone who says they don't have access to what you need to do, beautiful example right here. You can pretty much follow exactly what I've done. I like neat things. You don't necessarily have to type it, but I should be able to read it in your PDF. If it's chicken scratch, it's really hard for me to give you points because I want to give you points. Failing you guys is a huge headache for me. Even a B-, I have to explain myself to the department about why you would get that mark. So let's make my life easy by you guys getting a good mark on these projects, okay? So here's a very good worked out example for a column. Here are 3 worked out problems for you to take a look at. I can tell you that you're probably gonna do this for the beam. This is the easy one where it's just a uniformly distributed load. Now, I know the next question some of you are gonna ask me. I have joists sitting on a beam. What do I do? Do I have to do a series of point loads? I can tell you what we do in the industry is we often design those as uniformly distributed loads. Even though it's a series of point loads, we tend to cheat a little bit. And so these 3 beams here all have joists with deck on them framing into these beams. And you could reasonably say I have a point load and a point load. Fair enough. But what we often do is design this as a uniformly distributed load for all 3 of these. The hollow core coming into the beams is easy. It's pretty obvious that it's a uniformly distributed load. But for joists plus deck or slab, we often assume all of these would be a uniformly distributed load, okay? Trusses, I know the next thing you guys are gonna ask is, well, what do I do then? You just said to treat all of these as a uniformly distributed load. Well, for a truss, we often do the opposite. We would still have to check the members for a uniformly distributed load. But as the truss analysis of it, we will often assume it's a series of point loads at the nodes, where we take small elements of tributary area and draw point loads at the nodes to simplify our analysis. And that is all I would ask you to do in the project. So you can see that both of these would end up being similar. They'd have different loads on them because the concrete on metal deck has a different load than the hollow core. But I would treat the hollow core as tributary areas that cause a point load at the nodes on the top chord of the truss. And remember, the loads are coming in at the top chord of the truss because it's under our roof. So for most of you, that is like, I've given you the answers for the project. Like, it's super easy now, which means I can usually tell who hasn't listened to my lectures throughout the term very quickly when I glance at the projects. Okay. I have also given you guys, so I gave you, 3 more worked out problems here in this question set. And then I gave you a worked out assignment that has 4 more worked out problems. So if you're struggling for what to do for the project, you can go back and take a look. Last week, I gave you guys 8 more worked out problems, I think. So you've got 16 fully solved, worked out problems available to you on how to solve these method of sections for a beam and bending. And you guys get to assume the most simplified version of it, right? You get to assume it's a uniformly distributed load. So some good forever tips. Moment frames are a last resort. They're expensive and deflection will often govern them. You should know how to calculate maximum allowable deflections and lateral movement. So I just want to go back to that. So in the project, look what I've done here. Take a look at these. You can see that I've solved them, but I've also then written out what the allowable deflection is, or the maximum deflection we'd want to see. This sets us up well so that next term we're looking at what's the capacity for shear, what's the capacity for axial, what's the capacity for moment, and what's the actual deflection, what's actually happening, so that we can compare all of those things. So we've now done 1/2 of all of those equations, all right? And next year, we're gonna look at the other half of the equation. It's been fantastic working with you guys. I'm sorry that I didn't really get to talk to many of you in person, just a handful of you that I've seen around. Hopefully next year we'll all be back in person. I can't wait for that. What's really nice though is that if there's an emergency or something comes up, which tends to happen at least once during the term, I have the ability now to record a lecture for you guys. So you'll get all full 12 weeks of your lectures, which I think is really important for you guys. I believe you guys have all gotten links for course evaluations. Obviously, you guys can write and say whatever you want. I encourage you guys to go fill those out. It's a valuable tool for the administration, but it's also a valuable tool for me. I get to read those comments. Not only does the administration read the comments, but you guys might not know this, but your professors read the comments. It's anonymous, as it should be. You guys should have the right and the ability to express your views on things. But the professors do read the comments. So I know in particular, there has been a professor who's unfortunately had to read some very negative feedback. And I think there's somebody who's doing a really good job. And the big takeaway though, is they and me over the years, we really use those to see what we can do to improve our course. There's a lot of things I've added in. The fact that I use multiple colored pens directly comes out of feedback from the students. There's a lot of things that I've really tried to incorporate over the years. So you are more than welcome to say, I don't like math, this is dumb. Fine. But I can tell you that the administration and myself are going to laugh at that comment because the whole point of this course is to teach you that math. It's kind of mandated. The accreditation department makes sure I do that. So as much as you don't like it, I can't get rid of that. What is valuable is if you have a critique, to give us a suggestion of what can be done to improve it. I will often try to do what I can. I went and spent a bunch of money on a better camera and a bunch of better microphone for being able to do this stuff. So please don't think your opinions don't matter. And if they are reasonable and something that can improve the course, we'll do it. Now, I always get people that say, you've done too many examples, don't do as much, it wastes our time. And then I have other people say, there's not enough examples, you need to do more examples. There's not much I can do in between those two things. It's all about a balance. So again, you're entitled to your opinion and you should express your opinion, but just know that this is about trying to find a balance to meet all the needs of the course as well. So don't think about just yourself, but think about the kind of the cohort, about what's going to benefit the overall teaching of the course. And that's what I strive to do here. Over the next few days, for Structures 2, I'm going to be posting the lecture where we test beams. You guys won't know a lot of what's going on that, but it's one of the funnest lectures of the entire 2 terms, and we'll be doing it next year as well. But if you subscribe to the channel just because you like to get notifications that the lectures are posted, if you want and you're bored and you're eating popcorn one night, feel free to watch that one. Hopefully it'll be a nice day and I can get outside and test them outside. So Dave and I usually have a running commentary. It's kind of a fun lecture to watch. So there's the one from last year as well. So hopefully I'll see you guys all in person next term. I will be downstairs. I will be downtown for the comprehensive studio reviews. I'm not attending your studio reviews, but I am attending the comprehensive studio reviews. So I don't even know what dates yours are, but I'll be around on campus for those 2 days. So best of luck, stay healthy, and see you guys next year.